This is Radio TV Phono Nut, and in a recent repair video I used a crudely improvised battery eliminator to power a battery-operated tube radio, and I had several requests for a video on that particular battery eliminator. Well, as it just so happens, that was something that I put together probably 6 or 8 months ago. I don't remember, but I never did release the video, so since we have some demand for it, I'll release that. But before we do, I need to make a correction. The schematic I presented at the end of the video is, I don't know why I didn't catch it, but I didn't draw it correctly. If my electronics instructor from college saw that, he would probably revoke my electronics technology degree. But anyway, here's the revised one. We're using 2 low voltage transformers wired back to back, 12 volt center tap transformer wired to the back side of another 12 volt transformer, and we're using the 6.3 volt center tap for our low voltage, going into a bridge rectifier filtered by a 4700 microfarad 25 volt cap or 16 volt cap. That'll work. Going into an LM317T voltage regulator. Pin 3 is the input voltage, pin 1 is the reference or adjust pin, and pin 2 is the output voltage. So you can see the schematic. We have a 56 ohm resistor connected between pin 1 to A minus, and then we have a 220 ohm resistor connected between pin 1 in pin 2, and that'll give you 1.5 volts output for your filaments, for your tube filaments. And then for our B plus, there are several different ways we could do this, but I did what we could do with the junk I had on hand. Like I said, have the 2 12 volt transformers wired back to back for isolation purposes. And coming off the second transformer, we have approximately 120 volts AC going into a 47 ohm resistor, coming out of the resistor going into a 1N4007 diode. This is a half-wave power supply. I could have just as easily used one of those bridge rectifier modules. And then you see we go through a bunch of capacitors and resistors here. 33 microfarad for the first 2 capacitors and 22 microfarad for the last 2 capacitors, with a string of 1.5 k ohm resistors, and these capacitors should be at least 200 volts. And then the 39 k ohm resistor that we have paralleled with the output, that's to provide a load on the power supply, so in case it's plugged in with no radio plug connected to it, then that resistor will help bleed off the capacitor so they won't hold a nasty charge. And it also helps, even with the radio plugged in, it helps keep my voltage somewhere around 90 volts. That voltage is not very critical, but you know, just as long as it's somewhere around 90 volts, it'll work. Now this simple design will work just fine for your 1.5 volt and 90 volt tube radios. And like I mentioned later in the video, you do not have to use 2 transformers wired back to back. There are sufficient transformers made today that will provide, say, a 6.3 volt AC source and say 125 volt source to get your high voltage from. But like I said, this was strictly made using what junk I had on hand. Now before we get into the power supply video any further, I'll throw this at you. This is that little 1956 Motorola 3-speed tube record player that we recently did a repair video on, and we offered it for sale for a starting bid of about what I've got in it. Actually, $115. If I sat down and did the math, I might actually have a little more in it, but I'll be happy with $115. Stuck it on eBay, and all we got was a bunch of lookers and watchers and no bidders. And I think the reason for that is because on eBay now there's just so many Crosleys and Chinese garbage record players on there, that what few vintage ones actually get listed on there anymore get buried in the shuffle and they're not seen. So we're giving it one more round. $115. Buy it now. No bidding. If you want it, just click the button. And I've already had people tell me, especially in one of the Facebook groups that I'm in, that I'm out of my mind on the price, and this is a $40 record player at best. Well, quite frankly, before I take $40 for it, I just as soon take a sledgehammer to it and bust it in a million pieces. After all the time I've spent going through this thing to make sure it works like brand new, and all the money I've invested in it in parts to make it work like brand new, I find $40 very insulting. And no, I'm not going to EOL this thing, but if I can't get my price for it this time, it can sit right here in my collection. You know, sometimes I enjoy fixing this stuff up, and sometimes I like to pass some of it along to other folks and try to recoup some of my money. But if people would rather have a Chinese Crosley Cruiser for $59.95, then by all means go buy one. That seems to be the issue in today's world. All people care about is the cheapest possible price. They don't care about quality. But anyway, I'll give you another brief little demonstration of this. And if you want it, there's a link in the description. And if you don't want it, then that's fine too. My feelings won't be hurt. But as far as $40 in today's world, that's about what it's going to cost you to get a record player like this to restore. Unless you happen to find one locally, which these are pretty rare in my area. If you buy one off of the internet, and by the time you pay shipping, it's going to be $40 or more. And like I said, that's for one that's not even working. But like I said, if this isn't worth my price, then I'm sorry. Go out and buy you a Crosley Cruiser.
It's just Elmer's good. What makes a lady of it? Matilda, 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 she take me money and run Venezuela. When Sunny gets through, her eyes get gray and cry. Waving at the birthday stand, talk to my the papa this one brain. We started going steady and honest you do.
Alright, so we'll put this back in neutral. Turn it off, and there you go. So, amplifier has all new capacitors, a new silicon rectifier, new resistors as needed, volume control clean, cartridge replaced with a new static 81T with a flip-over LP78 needle. The mechanism and motor was clean. The automobile was rebuilt by the VM website, and there you go. If it's not worth what I'm asking, it can sit here. And if you took this to a audio shop to have it repaired, I can guarantee you wouldn't get it done for what I'm asking for this. So there you go. If you want it, there it is. This is Radio TV Phono Nut, and what you see here is what's left of a very crude power supply that someone made to operate the typical late 30s to early 50s farm radio that requires 90 volts and 1.5 volts. The design of this used the rectified voltage off of the AC power line for the 90 volts, and they had a D-cell holder in here for of course, a 1.5 volt D-cell for the filament power, which I've removed that battery holder because I needed it for something. Now I've drawn out a little schematic here of their circuit. We have our 120 volts AC coming in here. C1 is a 0.1 microfarad 600 volt across the line capacitor. R1, the fusible resistor, it's supposed to open if this diode shorts, is a 4.7 ohm. Coming out of our diode, we have a 50 microfarad capacitor going into a filter choke. Coming out of a filter choke, we have another 50 microfarad cap. And then we have R2, which is a 1.5K 2 watt, and the output of that goes into another 50 microfarad cap and into another 1.5K ohm 2 watt resistor, and finally a 30 microfarad cap, and that's where supposedly your 90 volts comes out. Now, I recall checking this power supply, and even under the load of a radio there was more than 90 volts there, so we need to tweak his circuit design a little bit. And he used 150 volt caps, which is cutting it close because the voltage could very well rise above that. I'd feel a lot better using 200 or 250 volt caps. Alright, I looked on the internet and found a more simplified circuit that more or less does the same thing. We have a 0.047 cap across the line. In this case, our feasible resistor is a 30 ohm. In today's world, 33 would be your most common value. Coming out of the diode, we have a 22 microfarad filter cap feeding into R2, which is a 2.4K ohm 2 watt. And lastly, we have another 22 microfarad filter cap, just a basic pi network here. Now this resistor across the output, they say if you want 90 volts, use a 4K 5 watt resistor, which 3.9K would be the closest common value today. Or if you need 67.5 volts, use a 2.5K 5 watt resistor. And I imagine 2200 would be the most common value for that today. Now, one thing I like about this resistor being across the output is when you turn the set off or disconnect the radio, or if someone invariably plugs the power supply in with no load across it, then this resistor is going to discharge these caps whenever the power supply is disconnected from the AC supply. This power supply diagram here could be very dangerous because these caps are probably not going to discharge in a hurry. Another thing that makes both of these designs dangerous is there's no type of isolation transformer between the AC power line and the power supply itself. And most of these battery type radios would have a hot chassis. Usually the A- or the filament supply is connected directly to the chassis, and the B- connects to one end of, say, an 800 ohm resistor, and the other end of that resistor connects to your chassis, which still, that's a dangerous situation. It could cause a shock hazard, or if you have your radio connected to an external antenna and ground, that wouldn't be a problem when using battery power, but using a non-isolated AC supply could create big problems. So, let's take this thing that somebody hacked together and take it down to the shop and see if we can redesign it and make it a little bit safer. I don't have any problem with the filter choke or any of this other stuff, but we're going to have to do some things to make this safer. And this newer Frontier capacitor multi-section cap, it's still good. This old 5030 General Industries cap, it's nearly dead. So, yeah, this needs to be gutted, and we need to just start over with it. Well, I got everything stripped off for the most part, and I was going to reuse this choke that he had, but I guess me moving the leads around broke them loose inside the choke, because now we have an open circuit, which is fine because we really don't need the choke anyway. That's a bit overkill. I can just put a resistor in its place, and we can use that spot to put the transformer or transformers that I'm going to use. Alright, here's our terminal strip with our diode and resistors on it. Those yellow wires will be going to another terminal strip, which will contain the filter capacitors. So I just put another 1.5K resistor where that choke would have been. And the filter capacitor values are not that critical. We can put 47s or 33s or 68s or whatever we can come up with. Alright, here we are. It's starting to take shape. All I really need to do is find a suitable isolation transformer, even if that means wiring two 6.3 volt transformers back to back. But right now we're going to plug it into our variable isolated AC power supply, and I found a 5K resistor that I'm going to use for a load, and we're going to check our output voltage and see what kind of component values we need to alter. Okay, at 120 volts input and a 5K resistor for a load, that gives us 87 volts. And of course, when we add the load of a radio, that's going to knock it down a little more. So I might want to up that resistor just a tad bit. But you notice when I turn it off, how quickly the caps discharge. And that's a good thing. Alright, using an 8K resistor, that gives us 109 volts. Now right now I'm going to rig up a D cell in here for the filament supply, and then we're going to go get a radio and see how it works under load. Okay, for our test subject, we have this Coronado radio from about 1941. It was made by Belmont. I can't remember if I released the video on this or not, but if I didn't, I will soon. It was in kind of rough shape when I got it, but it's been fully overhauled and the battery cable rewired and new antenna and ground wires and new speaker and all sorts of things. But we can use this as our test subject, which we'll do right now in just a few minutes. Alright, I'm powering the filament from this 1D cell, a carbon zinc battery. Let's just see how much the filament drags it down. 1.6 unloaded, 1.53, 1.54 loaded. Alright, now let's make our B plus connection and connect the meter and turn this thing on and see how much we get. Alright, 78 volts under load of the radio. Well, that was not what I intended to do. 78 volts under load of the radio, and 110 volts, we'll say, without the radio. So let's increase that resistor a little bit. Okay, I went with a 39k ohm 2-watt resistor, and I attached it to this terminal strip that he had used for something else, so I just went ahead and used that to put our resistor instead of cluttering it up on this power plug here. And unloaded, we're reading 145 volts. Now notice when I turn it off, and it takes a little while for those capacitors to discharge, probably, well, way less than a minute. But if that resistor wasn't in place to provide a load and someone flipped this thing on and turned it off, those capacitors would stay charged for a very long time because there would be no load there to bleed the charge off. And this resistor is just barely noticeable warm to the touch after it's been on for a while, so there's no danger of that overheating and catching anything on fire. The parts list specifies a 5-watt resistor, but they also specify 350 volt caps, which is a bit overkill. So yeah, this 2-watt resistor is ample enough to provide a load for this thing. Now, yes, I could have used solid state means of regulation such as Zener diodes, but diodes like to short. Resistors don't short so much. If anything happens, this resistor will go up in value, and even that won't be an issue if I replace this with a film resistor. Well, let me back up. It won't be as big of an issue. Now, this carbon comp resistor could very well go up in value, but still, it's not a huge big deal if it does. It's just providing load on the power supply.
Sheet music.
Alright, here we are running 95 volts into the radio, which is good with a 120 volts line, and I can lower the line input.
Eugene Robinson defended the toppling of statues going on far and wide.
There's 85 volts input, and we're down to about 100 volts. So yeah, this will work satisfactory over the wide range of AC line input voltages.
Was under the rule of the Democratic Party.
These monuments were generally erected around.
Now let's pull the plug and see how long it takes it to discharge with the radio as a load,
The South was
in addition to the resistor. Yeah, not any time at all. Now let's turn this radio off because I don't want to kill my battery. That carbon zinc battery is not going to last long with, what, 180, 200 milliamps of current being drawn on the filament line. Now this is the basic circuit you want for your B battery eliminator, but do not, I repeat, do not use this circuit as is plugged directly into the 120 volt AC line. You need to have an isolation transformer ahead of it, and that can be just a little small transformer from Antique Electronic Supply. You can take two 6.3 volt filament transformers and wire them back to back. This is not a high current demand device, so that'll do fine. In fact, I'm fixing to look through my junk and see if I can find a couple of 6.3, 12.6 or whatever volt transformers that I can wire back to back and have an isolated supply, and then we can take a tap off of the junction to build a little regulated supply to provide 1.5 volts for the filament and not have to rely on this battery here. Okay, here's what we need for the low voltage: a step down transformer that has it could be anywhere from 6.3 to 12.6 volts, but preferably 6.3. The regulator would run cooler with that lower voltage. And then we go into a bridge rectifier module, which you can also make out of individual diodes if you prefer. And then C1, the schematic I looked at was 4700 microfarad, but 22, 33, 47, 1500, that would all work, but 4700 would give you a little bit better filtering. And then we go into our LM317 voltage regulator. Pin 3 is the voltage input, pin 1 is the adjustment pin, and pin 2 is the output pin. And it's a very simple circuit. We have a 220 ohm resistor between pins 1 and 2, that's our feedback resistor. And then from pin 1 to ground we have a 56 ohm resistor, that's the value needed to give you about 1.5 volts. And then on the output, we have these three silicon diodes in series. Regular 1N4007s will be ample enough, and that's just a protection circuit because each diode conducts at about 0.5, 0.6 volts. So when you put three of them in series, that's roughly 1.5 volts. So if this regulator was to short, these three diodes would prevent the voltage here at our output from rising above 1.5 volts and blowing the tube filaments out. Now what we need to do is go look through my junk and try to find a couple of transformers that I can wire back to back to get isolation for the high voltage supply, and then we can use the junction of the two transformers for our low voltage takeoff for this little circuit. And yes, the LM317 will have to be on a heat sink. I'll probably use the metal chassis for that, since we're not using the metal chassis to reference anything else to, so we should be able to use that for a heat sink. Okay, I found two similar transformers. One has like a 12 volt secondary and the other one puts out like 14. So feeding AC into one, wiring them back to back, and we got 134 coming out of the other one. And I found every part I need except for the LM317s, and I know I ordered a bunch of those last time I built a little power supply, and of course, now that I need them, I can't find them. Isn't that the way it always works? Now, if I didn't need them, I could lay my hands right on them. Alright, I found two more, another transformer that gives us a closer match. We have this 12-volt transformer here, feeding the secondary of this transformer that we previously used. I think it came out of an old junk Caliphone record player. And that gives us 123 volts output, so that's more in line with what we need. So we're going to use these two transformers. This big one can be the input transformer, and this one here can be the output. Well, my soldering iron has already fallen apart. This new fine Weller soldering iron. JB welded it back together, lasted a few months, fell apart again. JB welded it again. Now I reach up to use it. It's cold as a cucumber, and all I'm getting is this display flashing. So yeah, I'm about done with Weller. Responds to nothing whenever I push any buttons. It's just sitting there blinking at me. So time to find another option. Well, poor planning on my part. I should have selected what transformer I was going to use and drilled the appropriate holes before I put everything underneath, but I didn't do that. So we soldered the transformers to the chassis, and since this is not something that I intend to be pretty in the first place, I'm really not worried about it. If this was something that I was really concerned about, I would have purchased a nice chassis to put it on and ordered the correct transformer and blah blah blah, but this is more or less just a time waster project out of junk box parts, so we're not too worried about what it looks like. Okay, I was forced to come out to the shop and do a little cleaning up today because it had gotten really bad to the point that the mountain of junk on my bench was blocking the air conditioner, and I've held off as long as I can this season without turning the air conditioner on out here. This high humidity is kind of making me irritable when I come out here to work. So I was forced to do some cleaning up, and look what I found, my sleeve of LM317s, and I also found a heat sink that we can mount it to. Okay, just to demonstrate something, I had plugged this in a couple of days ago when I last worked on it to make sure we were good up to this point with no load across the filter cap for the low voltage. Jumped up to about 19 volts there, and you can see it's been off for a couple of days and we still have 14 volts on that cap, so with nothing to bleed it down, it could take quite some time for that charge to go away. Okay, I've decided to make a little circuit change. Having 20 volts roughly going into that regulator and dropping it down to 1.5 volts, that's quite a voltage drop. And that regulator could probably handle it, but it's going to get kind of hot. So I decided to take off of the center tap of the transformer, which will lower our voltage a good bit, which will mean less voltage drop across that regulator, and it should run cooler. Alright, 9.4 volts unloaded, that's better, and that regulator will be a lot happier. Okay, I've decided I'm going to mount the regulator directly to the chassis itself, because since I've mounted everything else to the chassis, anywhere I drill a hole to attach the heat sink, there's a chance I could mess up something I've already done, and I don't want to do that. So this chassis is just going to be this will be reference to our 1.5 volt output, and we will just attach this directly to the chassis, and I have our connecting wire connected to each terminal, red, white, and blue, 1, 2, and 3. Very patriotic for the upcoming 4th of July holiday. Okay, here we are with the regulator mounted to the chassis. I did use some grease between the regulator and the chassis for better heat transfer. And we have 1.56, 1.57 volts. That's beautiful. Now we'll go get a radio and plug this sucker up and see how it does. So under load we have 8.8 volts coming into the regulator, or should I say going in would be more grammatically correct, and 1.57 coming out. So let's let it stay plugged in a while and just see how warm this gets. Okay, I tried this added safety diode circuit here, and I used my variable supply here, and yes, I made sure the diodes were good. It calls for 1N4006. Ours are 1N4007, which is just a little bit beefier diode. Well, it didn't do anything to lower the voltage. The diodes just got hot, so I'm not even going to worry about that circuit. As well as I have this IC heat sinked, I don't think we have to worry about it getting hot enough to short. So we're just going to let it go as it is. I've seen circuits with these 3 diodes wired in series on the output. I've seen other circuits that didn't have them. I've seen more circuits that didn't have them than had them, so we're not going to worry about it. Alright, we're plugged into the battery eliminator, and I'm using myself for an antenna right now. Right now I'm not interested in high performance. Just want to show you that the power supply is working. We're holding our own 1.57 volts even under load. That's perfect. And our B plus is running 84 volts, so that's within range. Yeah, it's a little low tonight. Air conditioner's running and all that. So, but yeah. As long as the B plus is between 80 and 100 volts, the radio will operate satisfactorily. Alright, and take note, not one bit of background hum, so this thing is well filtered.
Decision was reversed. Right, those
Alright, I'm not going to do a band scan tonight. This radio is not the subject of this video. Just to show you that this thing works is the subject of this video, this crude little power supply that I made. All I'd have to do to this is add a fake digital timer to this and dig around in my box under here and find some of the old dud multi-section cardboard case filter capacitors, tape about 3 of those together and attach that to this, and it would be guaranteed to freak out airport security, I can tell you that. Alright, here's my crude schematic of how I obtain the results that we have. We have our input transformer, which has a 12.6 volt center tapped secondary, and then we have our next transformer that has a 12.6 volt uncenter tapped secondary. We have the 12.6 volt secondaries connected together, and I'm using the center tap on the first transformer for the low voltage supply. Alright, so coming off of our second transformer, go into a 47 ohm resistor, into our diode 1N4007 or etc. And then a 33 microfarad filter cap, a 1.5K 2-watt resistor, another 33 microfarad filter cap, into another 1.5K 2-watt resistor, into a 22 microfarad cap, into another 1.5K 2-watt resistor, finally into the last 22 microfarad cap, and all of those really need to be at least 200 working volts. And then we have a 39K ohm 2-watt resistor as our load, and then that'll give you enough B plus to operate your radio. And then that resistor will provide some protection if this power supply is plugged in unloaded. The resistor will discharge the capacitors when it's unplugged. And then coming down off of our 6.3 volt tap on the first transformer, we go into a bridge rectifier module, which you can make out of individual diodes. Coming out of that module, we go into a 4700 microfarad capacitor. And then as you can see, our voltage input to the LM317T. Input is pin 3, our adjust pin is pin 1, and our output is pin 2. We have a 220 ohm resistor between pins 1 and 2, and then a 56 ohm resistor between pins 1 and ground. That 56 ohm resistor determines your output voltage, so that's the value we need for 1.5 volts. Now you don't have to use back-to-back transformers like this. There are suitable transformers, such as this Hammond 229A12 that he mentions on his schematic. And as far as this 3-diode arrangement on the output, we're not worrying about that, because whenever I tried it on my little test power supply, they didn't hold the voltage at 1.5 volts, and they ran hot in short order, so we're just not going to fool with that. And like I said, this is not meant to be pretty. This is something I would never release to anybody. This was just make a pile of junk into a power supply.